Hi students, welcome back to DSP online video lectures. From this video lecture onwards, we will start the discrete Fourier series representation of periodic sequences. So essentially the frequency domain representation of um, discrete time periodic signals. That's what we are going to do. Okay, so let me move on to desktop sharing mode, and let me move on to the notebook mode. Okay, so before discussing about, so this is referred to as discrete Fourier series is what we are going to discuss. Okay, yeah, anyway, before that, let me just give you, let's have a recap of what is it that we have. So what are the transforms, for example, that we have discussed so far? Okay, so that's what let's take a look at. So what are the transforms that we have discussed so far, that we have studied so far? Let's take a look into that. To do this, let's classify things into a slightly organized way. Let's say we had studied, for example, in terms of assume that we're talking in terms of 1D signals. So I'm writing for convenience as time, although it could be like multiple dimensional signals, multi-dimensional signals. On one side we studied continuous time signals, right? And another side we have studied discrete time signals, particularly during this semester. And then in terms of the periodicity, if we classify them, we could classify them, the signals, as periodic, and signals that are not periodic, we refer to them as aperiodic. So these are the things that we have studied. So let's try to categorize whatever we have studied so far into these blocks. Okay, so if you recollect from the last semester, the signals and systems course, you have studied the periodic signals, the frequency domain representation of that. So that was what you got there was Fourier series, continuous time Fourier series is what you started with, right? Continuous time Fourier series you studied, and then you move to a periodic signal frequency domain representation in the same course. That is when you studied continuous time Fourier transform, and then you have studied the generalization of that, and that turned out to be Laplace transform. That's what you have studied, right? And then in this semester we started with discrete time periodic signals, and they represent, so those are the ones. So what we studied here is discrete time Fourier transform. Okay, so what we have not yet studied is a discrete time signal which is periodic. Okay, that's exactly what we are going to study now, that we refer to as discrete time Fourier series. Okay, discrete time Fourier, just to distinguish it from continuous time Fourier series, you call it as discrete time Fourier series. Okay, or we abbreviate it as DFS. So this is what we would be studying in this class and few more subsequent classes. Okay, so what is of interest now to us is a discrete time signal and the signal being periodic. Okay, that's our interest for this class and few more subsequent classes. Okay, so then so what is the signal that is what do we mean by what? So what do we mean? What do we mean by saying discrete time? What do we mean by saying discrete time periodic sequence? How could we, or in other words, how could we represent a discrete time periodic sequence? That's the question. Yeah, this is very simple. Let's say first thing, let's write it as x of n. Later you would see that we would be making a switch between periodic signal and its equivalent in a finite signal. Okay, what I mean by equivalent, we will come back to it little later. But to distinguish them from now onwards, another thing that we would consistently do is to represent a periodic sequence with a tilde on its head. So when you see tilde for a signal, that means it is periodic. Okay, so how can we, suppose I say that it is periodic, the sequence is periodic with a periodicity of capital N, then what do we mean then? So that means x tilde of n be equivalent to x tilde of n plus let's say r times n, where this r could be in any integer. And then you could see that the value of n repeats for every capital after every capital N values, and that's what we mean by a discrete time periodic sequence. Okay, yeah, the closest one, or the one which we could start imitating to develop this discrete time Fourier series, is in fact the continuous time Fourier series. Yeah, we are following. Yeah, by the way, let me just complete here. After ZTFT, we have also studied here Z transforms, right? That's also we have studied. I forgot to mention that. Okay, coming back, we start with a continuous time Fourier series. Okay, if you want me to call it as CFS, okay, similarly, I don't know what we called it earlier, but that's fine. Okay, so let's start with the frequency domain representation of a continuous time signal. Let's start with that. So frequency domain representation of a continuous time. We are also specific about signal being periodic, so continuous time periodic signal. So that's what, let's take a look into that. Hope you could recollect this, how we have done it. Let me write and the expressions first. Synthesis equation first. X tilde of t, again as I mentioned, for continuous time also use tilde to represent the periodic continuous time signals, right? That you have a discrete set of harmonics. The moment you are taking harmonics of the fundamental frequency, let's call that fundamental frequency of this periodicity as capital T. So you need all harmonics of that frequency to represent the signal. The weighting factor, let's say, be given by a subscript k. I am varying k from minus infinity to plus infinity into, you would like to express them as complex exponentials, so e power j times the frequency. I could have written as omega, but let me write it in terms of t, so that omega will be equal to 2 pi by t, okay, into k times t. So at any particular value of t, you are representing the signal as the fundamental, as the complex exponentials, and those complex exponentials having for varying values of integer values of k has the fundamental frequency as well as the frequencies that are the harmonics of that frequency. Okay, that is how you are representing the signal. Okay, then what would be this ak value? Ak, well, the signal being periodic, you do it over one period to find it out. Okay, integration or one period, it could be 0 to t as well, but let me write the conventional minus t by 2 to plus t by 2. You take the original signal x of t. Okay, now in this analysis equation you would be having minus sign here instead of the positive there, compared to the x tilde of t synthesis equation, times k t. Okay, and this integration is with respect to t. So these were the expressions, isn't it? Now let's try to get an analogy of this discrete time and continuous time. Let's try to draw the analogy of continuous time and the discrete time. Okay, on one side let me have continuous time signal, and how that gets transformed when I move on to a discrete time signal. What could be an equivalent one there? Okay, so this is what we will do. For example, here x tilde of t, you would be using the variable t here. The moment we are moving to the discrete time domain, we are typically using n, which is an integer. T is a continuous variable that can take any value. The periodicity, as I mentioned here, is t. Usually the periodicity, capital T is what you are using. So in the same manner, we use capital N here to represent the periodicity. Okay, and the periodic signal, we use x tilde of t. Okay, and well, the signal now is x tilde of n here. Square brackets we use instead of those brackets for to distinguish it from the continuous time signal. Then you have those complex exponentials. Say for example, this is let's say if you have e power j 2 pi by t into something like kt, which you are having there. K is telling you the kth harmonic there. Okay, what could be the equivalent expression on the discrete time? Say complex exponential j times 2 pi by, your periodicity is capital N here, not the capital T. Okay, let's the harmonic, kth harmonic represent with the same. Instead of t, the parameter here is n. Okay, now what we would do is, let's make a more deeper analysis. Let's make a more deep analysis of this complex exponential before we start writing the frequency domain representations. Okay, so what we would do now is, let's make analysis of the properties of, also let me write it like the complex exponential, k representing the kth harmonic. Okay, and its value at n. Okay, let me write it as that. Okay, for in capital N being constant, which is representing e power j times 2 pi by n times kn. That's what we would like to study now. Okay, the first thing let's do is, how does this complex exponential behave? So let me first do this out. E of k times n plus any multiple of it by an integer factor r. It's very easy to see that in fact what would be that equivalent to. That's what, let's try that out. So this would be equivalent to e power exponential of j times 2 pi by n into the harmonic value subscript is indicated by that, that's k, and the value at which you want to compute the index is n plus r times n, right? And you could see the second term here, n could cancelled out, and you could separate that term and keep that as a multiplication factor. So that would give you e power j times 2 pi times k times n, and n are getting cancelled, another integer r is there, right, into e power j times 2 pi by n into, what's the remaining, the first term, kn. Okay, and what is this value? Of course this is equal to 1 because k and r are integers. The moment you are, say, e power j0 is here, any multiple of 2 pi would come here. So if you have any 2 pi into any integer multiple p would bring you to again the value 1 here, isn't it? E power j0 is cos 0 plus j sin 0, right? So this is nothing but, well, this expression is nothing but ek of n, is it not? E power j 2 pi by n into kn. What does this mean? Ek is representing the kth harmonic, and that ek n plus rn being ek of n means, what you could say is each harmonic is periodic, and that periodicity is equivalent to the same as the periodicity of the input signal in discrete time sequence n. So what I could say is each harmonic harmonic of that exponential is, each harmonic is periodic with a periodicity of capital N. So smallest value where it repeats is what you call as periodicity. So that's for r equal to 1. So each harmonic is periodic with a periodicity of n. So now you could see here the variables k and n in the ek of n in this expression could be exchanged. So you could already sense something from there, what could be another property that you could get here. Okay, so what I would like to see now is, what about kth harmonic is there, but the any integral multiple of that harmonic by n of, so at the same value n I would like to compute. So what would be that value? Well, you could write it in the similar way. So this is equivalent to e power j times 2 pi by n. Your harmonic value is k plus rn. Again your r is an integer, okay, and small n. So then you separate in the same way we did, and that you would end up with that as e power j times 2 pi by n into r times n times capital N, right? So then this n and n gets cancelled. So I could simply write it as 2 pi times rn. So instead of writing one more expression, just let me write it right away here. J times 2 pi r, right, rn, which is going to be 1, multiplied with e power j 2 pi by n k times n, correct? And this in fact is equivalent to e subscript k of n. This is again another very important result here. What does that mean? So the earlier result is telling you that each harmonic is periodic, and this is telling you there are only n distinct harmonics. So after that, this k, so you could think of it as, for example, if I have, this means that E0, okay, let me use the same color here, I'll use it slightly different. So that implies, for example, my k equal to 0, I take it, okay, E0 of n is equivalent to, what is that? For example, you take r equal to 1, that tells you En of n. And I take, let's say, E1 of n is equivalent to En plus 1 of n. Does it not? So that tells you, and there are only so this you could go till En minus 1 of n if you want me to write that, okay. So that would be equivalent to E, what should be that? So you 2n minus 1 of n. So k plus, here I have rn, that's we are adding 1, so 2n minus 1. So after that, if I write here En of 1, that's already equal to E0. En plus 1 is already equal to E1. So what could I infer here? This means that each harmonic, there are only n distinct harmonics. There are only n distinct harmonics. This is another very important result, okay. So with these are the two results that we make use now to write the expressions for the discrete time Fourier series, okay. I hope this is clear so far. So what we did is, we started with e power j 2 pi n by n is something we could have in the expression, and then we made analysis of it. We arrived at two results. All these harmonics are periodic, the first result. Second result, there are only n distinct harmonics, the remaining are the same. So now we would write the expressions for definitions of DFS. So expressions for DFS is what we are going to write now. Okay. How do we write? Let's take an inspiration from the expressions of this. Okay. Whatever we have here, right? So let me yeah, it would be good to have them side by side. Okay, so let me see if I could copy them there and paste there, so that it becomes easier to do a similar stuff there. So let me just select this. Okay, hope I could copy that file. Sorry, yeah, should hopefully by keeping it here, copy, and then let me check if I could paste here. It would be great if I can. Yeah, great, we could do that out. Okay, so these were the expressions that we had computed, we know, for the continuous time. Okay, these are for CFS. These are the expressions for CFS expressions we already know. Okay, now let's see continuous time Fourier series. For DFS, we now know that it should be x tilde of n. Okay, now we know that there are only n, their harmonics are varying from minus infinity to plus infinity, but in fact there are only n distinct harmonics. So I could only write here k equal to 0 to n minus 1. Anyway, after that they would repeat. Okay, and then anyway these coefficients ak, which I would be getting, is also periodic with a periodicity of n. So instead of ak, let me write it here again, this being periodic. Okay, I am writing it as x tilde of k e power j 2 pi by, instead of capital T I have capital N, k times, instead of t I have n. Okay, one more modification would be there. For example, you look at it this way, this 1 by t, I could have taken it here in the summation itself, x tilde of t, that's also is fine. Okay, this is just I am trying to give an intuition and doing that. All that would happen is then ak, if I had written, see, one of them is what we are defining, the other one we are deriving. Okay, so if I assume that I have defined x tilde of t as 1 by t outside, I would get rid of this thing. Okay, for some reason which would be obvious to you a little later, I would like to incorporate here that 1 by t in this definition. Okay, that's the expression for this, the synthesis equation we call it, right? That's for DFS. Okay, and then how about this x tilde of k now? Well, this 1 by t I moved it there, not required. Okay, and then x tilde of t is a continuous variable, you had it from minus t by 2 to plus t by 2, but this is a discrete time, x tilde of n is discrete time sequence, its periodicity is n, so I need to do it from 0 to n minus 1. So one period is equal to, here one period means n equal to 0 to n minus 1, and then I have just like there x tilde of n, and here e power minus j 2 pi by n times k n. These are the equations for DFS, which we will be using quite a lot from now onwards. Anyway, if you want some naming for it, the conventional naming is, this is referred to as synthesis equation, because you are synthesizing the input signal with the help of those fundamental discrete time sequence with fundamental frequency and it harmonics, and this is called as analysis equation. One is synthesis and another is analysis equation. Okay, so that's all. These are the equations. So just to repeat, x tilde of k, okay, this is like the coefficient a subscript k there. Okay, 1 by t has been accounted by 1 by n there. again we will do in next class or the class after that a derivation, detailed derivation, but before that I want you to have some intuition for these equations. So that's why I'm trying to compare with CFS and write the equations for DFS here. Okay. Yeah, it's time to take a pause and spend few minutes here to see something unique that has happened the moment we moved to DFS, which was not the case earlier. Okay, to understand that, let's try to again do some stuff which we had done earlier. So you had, for example, in the time we did it for continuous time signals we have dealt with, and then there is this discrete time sequences we have dealt with, and then we consider two types of things. One is periodic and another is aperiodic. Okay, let's try to look at the characteristics of the frequency domain properties. So that's what we would like to take a look at here. Okay, so let me call here this is as so what we are going to analyze now is the frequency domain properties of frequency domain properties of the transforms that we have discussed so far. That's what we are going to do now. Okay, so let's take a quick look into that. What happened to continuous time Fourier series earlier? Continuous time Fourier series that we have discussed. Just a minute, let me finish that out. Okay, that's good enough. Right, so continuous time Fourier series is right away here. What was the property of it? The values, the coefficients which you have got, this is the frequency domain representation there, and it has values only at discrete points of time. So what you have here, the properties, they are discrete. And then look at, is it periodic? No, this AK has no periodicity, so that's why you are varying K from minus infinity to plus infinity, and so this is aperiodic. And what about the CTFT? If you recollect, well, CTFT is x of j omega. That was a continuous, the transform in that domain also x of j omega was continuous, is it not? And what about the periodicity of it? No, that's aperiodic only. There also there is no periodicity there. That was aperiodic. Okay, same case with Laplace. And then you come back to the DTFT, that's discrete time Fourier transform. That is where this is x of e power j omega. Omega is a continuous variable. It was discrete in the time domain but not in the frequency domain. So you had here this being continuous, okay, but it was periodic with a periodicity of 2 pi, right? So this is periodic with a periodicity of 2 pi, right? Now what happened? Now DFS, is it discrete? Yes, it is discrete. It has only values at n equal to 0 to n minus 1. So this is discrete without any doubt, and this is periodic. Okay, so this is what we have it right now. So this is what we are analyzing. So now this is both discrete and periodic. Why is it interesting? Is there any way that you could completely like, even as you consider a simple thing of saving all the values of omega, for example, as long as it is continuous, there is no way you could store all the values of omega if you are doing it through a programming. Okay, so that way this won't be, you won't be able to deal with this, right? You won't be able to, as long as it is continuous, this you cannot store, DTFT you cannot store. And although this is discrete, being aperiodic, it has infinite number of values, so that would never so in principle it can happen that it could never end up. So only here, this being periodic, you could always keep track of those things. Anyway, this is just a tip of the iceberg. We will discuss it in more detail when we move on to DFT. Again, discrete Fourier transform. This, by the way, the discrete Fourier series forms the basis for discrete Fourier transform. It's in fact on in all your programs, to find out it's the frequency domain response, what you would be using is discrete Fourier transform. But for that, discrete Fourier series DFS is serves as the basis. So this is what the properties of it. Okay, hope things are clear to you. So what you have here is unlike that happened anytime earlier. So you had your both your input and output are periodic. Okay, both the signals are periodic. Of course, that happened so with this DTFT also, but so that this is having a combination of both discrete and periodic. Okay, by the way, you could also see some duality between periodicity and discreteness, if you notice here. Okay, as if the signal is periodic, okay, this is discrete, it's Fourier in the time domain, so whichever is in green is in the time domain. In the, if it is periodic for a reason, this would be discrete in case of the frequency domain. And also look at when your signal is discrete, that its frequency domain will be periodic there. Okay, so this again is not very difficult to get an intuition for it. We in fact have the built the basis for the same while we are discussing the sampling, so that you could easily comprehend why is it so. Okay, so with this I would let me move on to just a minute. Right, so let's stop here for this video. I want to keep it around 30 minutes. Okay, in the next video I'll be going to discuss about the derivation, a formal derivation followed by some examples. Okay, yeah, thanks for watching, and yeah, see you in the next class.